Hey everybody, welcome back to Binary Adventure. So in this video, I want to actually dig into the details of how AddressSanitizer actually works. I think a lot of people have used it, maybe not a lot, but a good number of people have used it before, and we've been demoing it on the channel. And I sort of explained how some of it works by explaining what's going on right here, in a cursory way. But if you're like me, you get curious and you want to know more details of how something works. So I'm going to give you the TLDR up front, and then after that we're going to dive into exactly how the thing works. I have the AddressSanitizer paper by the authors up and ready to go, and we're going to kind of go through that. Now the paper is 10 pages. It's not too long, and it actually is pretty concise, although I think the first 3 or 4 pages they actually go over sort of the weaknesses of other memory checker programs like Valgrind and things. They basically present a case against those, and why AddressSanitizer could be better. But they also talk about some of the weaknesses of AddressSanitizer too, which hopefully I'll have time to go into. So it might have been a good idea to do this first, but I wanted to dive right into how AddressSanitizer actually works in a practical sense in the first few videos. But if you're interested in how it actually works and what's going on under the hood, then without further ado, let's get started. So I want to draw your attention to this area here one more time. The actual error here is not really that relevant, but so we discussed before that AddressSanitizer often, not always, but often shows you a diagram that looks like this. And I talked about how it's kind of strange because it looks like a regular hex dump, but the memory addresses are different from your program's memory addresses. And on top of that, these 0 bytes are not actually 0 bytes. These are addressable bytes, which means that your program has the right to access them, write to them, read from them, etc. Your program can use these bytes that are marked as 0 here. So as the legend says, and as we talked about before, each one of these bytes here actually corresponds to 8 bytes in your application. So let's step back and think about this for a second. So this area is what they call shadow memory, or shadow bytes. And what it is it is a memory section that AddressSanitizer has reserved and allocated for its own uses internally. And what it does is it stores metadata and information about the state of your program's memory. So once again, what shadow memory does is it is other memory that stores data about your program's memory. And if you think about it, it makes perfect sense because, without even knowing the details of AddressSanitizer, if you just used it, you know that what it's doing is it's instrumenting your program in a way such that when your program does something that you don't intend for it to do with memory, it's able to find that. It catches it, and it immediately aborts the program and displays an error message like this, okay? And it stores backtraces and things like that as well. So just fundamentally, that means that AddressSanitizer has to store information and reason about your program's memory to be specific. And so it needs its own memory in order to do that. And so that's what the shadow memory is. They use a lot of fancy terms, and some of these terms are not necessarily created by them. If you look them up on Google or something, you'll see that these concepts have existed for some time. But AddressSanitizer uses a lot of these terms, and it can be a little bit confusing as to what they really mean. Their documentation, in my opinion, doesn't really explain a lot of these terms that well. They just kind of assume that you know them. And so that's what shadow memory is. And if you think about it even further, in order to do that, well, that when you use AddressSanitizer, you have to supply the compiler with a flag. It says fsanitize equals address. So what that implies is that the compiler is doing some work in order to implement AddressSanitizer in your program, which means that AddressSanitizer is actually being built into your program. It is essentially it's injecting itself into your program via the compiler, and one of the things that it actually injects into your program is an entire runtime library and a runtime, which essentially means that it's a bunch of code that runs alongside your program and in your program when your program's running, but it also is, there are references to it, and there is code that AddressSanitizer injects before the program's running, even just on disk. So there's two components to AddressSanitizer, which we'll get into later. But just looking at this one more time, so I want you to understand a concept here. So if every single one of these shadow memory bytes can represent 8 of your program bytes, there's a couple of things to note here. The first thing is that the reason why they did that is much like any other C programmer would do, especially on an embedded system or other systems, is just to save space, right? What they realized is that all modern memory allocators allocate memory in at least 8-byte chunks, not 7, not 5, not 3, 8. And we all know why that's the case. At least it's 8 is a power of 2, and we're usually working with powers of 2. We're dealing with pages. The CPU likes powers of 2 and things like that, right? And so what it does is, or what they figured out basically, is that if we're looking at an 8-byte chunk, we can represent everything that's needed in a 2-digit space like this, or in 1 byte, essentially, right? And so what they did, let's see, I'm going to pull up something else here. I'll pull up a page just to show you. Or actually, I'll just use the terminal. So let's use Vim here. So what they did is they said, okay, let's say we have, I'm just going to write out some program bytes, right? So let's say we have bytes 4F, 67, 89, 99, 12, 56, 78, 99. Let's say we have these. This is 8 bytes of your program's memory. Okay. Now let's say that all of those bytes are addressable by your program, meaning that you've malloced them, or there's stack memory that allocated for them, and so on. So what's going to happen is that AddressSanitizer shadow memory is going to read out as 00 for these bytes. Now let's talk about another scenario. Let's say that you have this time 4F, 67, 89, 99, and then there's some other bytes here. Let's just represent them as FFFFFF. And everything starting at this FF here, right, is not addressable by your program. So your program, we're at the end of an array or something, and these are the last 4 bytes of the array. And then after 99, this memory is not allocated to your program, right? So what they realized is that they can represent this as 0, 4, because they can say, 0, 4 means that there are 4 bytes here that are addressable by your program, and the rest of the bytes that are up there are not, essentially. So, now if there was only 3 bytes, let's say this 99 wasn't here, and instead it was, as part of the non-addressable space, we'll say, they would put 03 there. And then anything that starts with an F in shadow memory, such as all those codes over there that we saw, let's go back up here. So see how there's like FA, FD, F1, F2, F3, F5. Anything that is a negative number or starts with an F, essentially, it's read as a negative number and explained that way in the paper. That is not addressable by your program. And so what they figured out is that, hey, we could basically store data about, so let's say all of these are not addressable, right? So all 8 of these are not addressable by the program. I think I might actually put one too many there. Yeah, so let's say all those are not addressable. So now the question becomes, okay, this isn't addressable, so it's going to start with an F in shadow memory. But then, what type of not addressable memory is this? Are we talking about a heap? Is it heap memory? Is it stack memory, which could be 1, 2, or 3, or 5, right? So they're just encoding different metadata about the memory in your program in order to instrument and understand the program, okay? So that's sort of how that's working there. That's the reason why they do that. They realize that, hey, if we only have 8 bytes at a time of actual program memory, all these states can be represented in just one single byte of shadow memory, okay? Now, the other thing that is interesting that they do is that they actually take, so there's a rhyme and a reason to all this, to these actual shadow byte addresses here. They're actually, if you do some math to a regular program address, such as this 603.000000023, and you perform some math to it, it'll spit out an address that looks like this. So these addresses are basically encoded, and they're based on your real program's addresses. So these aren't just randomly chosen addresses right here, this CO6. And that's kind of how the shadow memory is created. So so we've covered that. Shadow memory is basically memory that stores metadata about your program's memory. And one more thing I wanted to sort of explicitly state here is that what this means is that AddressSanitizer, by definition, will take up 1/8 of your program's memory. Because for every single 8 bytes in your program, there's 1 byte in shadow memory that it needs. So if you look at the memory layout of your program, or the memory consumption for your program without AddressSanitizer, and then you turn AddressSanitizer on, it's going to be it's going to add 1/8 of whatever your program's memory usually was to that. So that's what's going on with the shadow byte situation here. So now I'm going to go over to the paper, and I'm going to kind of scroll through the paper in a few different areas, and we're just going to cover a couple of really kind of neat little points. So the first thing to note here is it says AddressSanitizer consists of 2 parts, an instrumentation module and a runtime library. And this is kind of what we talked about a little bit earlier. The instrumentation module modifies the code to check the shadow state for each memory access and creates poisoned red zones around stack and global objects to detect overflows and underflows. The current implementation is based on LLVM compile infrastructure. The runtime library replaces malloc, free, and related functions, creates poisoned red zones around allocated heap regions, delays the reuse of freed heap regions, and does error reporting. So let's kind of break that down a little bit. And by the way, you could thank these people right here, these guys, for making this. Konstantin, Derek, Alexander, and Dimitri. Okay, so let's dive into what that is. So let's think about this again. The instrumentation module is doing most of its work statically. That's the thing when you're saying fsanitize equals address, because global variables, static variables and things like that, they can be instrumented entirely on disk. And then when the program is loaded up, it needs to use this runtime. And so the instrumentation module, what it also does is it places kind of like placeholders around the stack variables, and we can look at that in a little bit because it shows it down in the paper a little bit lower. But it places these red zones basically around stack variables so that when the program loads up, then those stack variables that AddressSanitizer has created as red zones are also around your regular variables. And it's basically like almost like a guard page or something around your variables, guard variables, okay? And the runtime, obviously what it needs to handle is anything that happens at runtime in the program when it comes to memory. And so what it's going to do, as it says here, is when you call malloc in your program, AddressSanitizer actually replaces that malloc with its own malloc. And its malloc does stuff a little bit differently. It adds what's called red zones around your allocation. And it also, in one of those red zones, it stores the backtrace of your program's stack frames. So that way, when the program does abort, it can give you that nice backtrace, because with inside of the memory that AddressSanitizer is allocated in the red zone, it is able to use some of that memory in order to store the backtrace and information you could use for debugging, which is kind of what it talks about here. So what a poisoned red zone is, and we'll show that in a second, but what a poisoned red zone actually is it's an area or a region of memory that if your program tries to access it, it's going to flag AddressSanitizer and say, hey, it tried to access this area and this area is off limits, and then AddressSanitizer's code is going to abort the program and show you an error. It's like a guard zone around your memory. That's literally all it really is. So let's actually go down a little bit and start looking at some of this stuff. So this is where they talk about. Okay, so now we're getting into the good details here. So this is where they talk about what I just said about how there's the different states that can be represented of your program's memory inside of 1 byte of AddressSanitizer shadow memory. And then they talk about the algorithm that they use, which basically is this right here. So they take your program's address, they do a bitwise shift right by 3, and then they add it to some offset, and that's what gives you those shadow memory addresses, which in our program started with C. Okay, and then they go into some details about that. But what I wanted you to see here is that, so here we go. So see how it says RZ1, MEM1, RZ2, MEM2, RZ3, MEM3, RZ4. So it says for n regions, we allocate n plus 1 red zones. So if your program has 5 regions, it's going to have 6 red zones around those regions, such that the right red zone of one region is typically a left red zone of another region. So remember how back at the terminal here, it talks about a heap left red zone. So in that case, that would be like, for example, for MEM1, the left red zone is RZ1. For MEM2, the left red zone is RZ2. For MEM3, the left red zone is RZ3, and so on. The left red zone is used to store the internal data of the allocator, such as the allocation size, thread ID, etc. Consequently, the minimum size of the heap red zone is currently 32 bytes. So what they're saying is that they need to store 32 bytes of metadata in there. So the smallest that a red zone could be is 32 bytes because they have to at least store that information in there. However, red zones are often bigger than that because that can help with detecting memory problems. And it says this internal data cannot be corrupted by a buffer overflow. So you can't overwrite a red zone the way that they've done this. And you can't, otherwise you'd be able to mess up AddressSanitizer itself, and then it wouldn't be able to help you, because such underflows are detected immediately prior to the actual store. So they have an algorithm in AddressSanitizer that before it actually writes any metadata, it makes sure that the red zone there is intact. And then it says the free function poisons the entire memory region and puts it into quarantine, such that this region will not be allocated by malloc anytime soon. So the thing is that in order for them to try to detect things like use after freeze, they want to delay any type of memory recycling as long as possible. They can't delay it forever. So if you have a use after free and you've done a whole bunch of other memory allocations in between there, they actually say later in the paper that AddressSanitizer may not be able to help you there. But what they want to do is try to, almost just like occupy as much free memory as possible, and keep it quarantined and poisoned, so that if your program tries to access that memory, it will flag and abort and give you that error message. And then it says, like I talked about earlier, malloc and free record the current call stack in order to provide more informative bug reports. So that answers the question about how AddressSanitizer gives you that backtrace. Okay, so now we're going to get into some cool details here. So they're saying let's say you have a function in your program, and you're going to use AddressSanitizer with it. And this function, it creates a stack array called char A10. And then it has some other stuff going on. Okay. AddressSanitizer is going to turn your function into this. So what it does is, just like I mentioned earlier, is it's going to place a 32 byte long red zone called RZ1 before your array. Then your array is going to be here. And then it's going to place another red zone, RZ2, after your array. And you can see here they do some math. So it's 32 minus 10 plus 32. And they do that because here's 32, and then 10 is for your array, and then they add 32 to it for this red zone here. Okay. So in this case, it's going to be 22 plus 32. So it's going to be 54. Okay, so now here's that algorithm that we looked at earlier. So where it says unsigned star shadow equals unsigned star long RZ1 shift right by 8 plus offset. So what they did is they took the first red zone, they bit shift it right 8 times, and they add this offset to it. And then, so you can see that they're just setting, so they're taking and setting this address that was created here, which ends up being the shadow memory address. They're creating red zones here and setting them as FFFFFFFFFF. Because remember how I said it when it's set all as Fs like that? That's how AddressSanitizer knows that the area is quote unquote poisoned in the shadow memory. So again, if your application has bytes that have FFFFF, this doesn't matter. But within the shadow memory region that AddressSanitizer uses, this has special meaning. And so you can see how that ends up actually working out here. So red zone 1 is here. The array in the red zone is here. So again, this looks actually just like that diagram that we looked at in the terminal. And what I showed you in Vim here. Because just like how here we have 8, 16, 19 addressable bytes here. In this case, what we have is 8 plus 2. We have 10 addressable bytes, right? So the rest of this is all poisoned red zone. So FFFFF is poison red zone, poison red zone, poison red zone, poison red zone. And then, boom, lo and behold, this represents 10 bytes of your program here. And look, that's what the size of your array was. So, to summarize, AddressSanitizer in its shadow memory surrounds all of your memory with these poisoned FFFF bytes. And then the instrumentation checks and it knows when you go and try to access those bytes. And then it just shows you what happens, if it needs to unpoison them. And then one thing it tells you is here are some of the weaknesses here. So the instrumentation scheme described above may miss a very rare type of bug, an unaligned access that is partially out of bounds. So if you have, so AddressSanitizer is used to working on like memory that is aligned, particularly to powers of 2, like 8, 16, 64, etc. So if you start doing some crazy stuff with memory that is unaligned and it's only partially out of bounds, it's telling you that it may not be able to find that. So you can see here that they knew up an int, C++ apparently, so they knew up an int array of 2, and then they take a pointer and they add 6 to it, and then they set that to 1. And it says access to range 6 to 9. So it says currently we ignore this type of bug since all solutions we have come up with slow down the common path. And so let's talk about another thing that it's not so good with. It says, first of all, AddressSanitizer has no false positives. So that's really cool. Let's see what else. Yeah, there's really not too many things it can't handle. I'll link an article in the description giving you a couple other things that it apparently doesn't really handle too well. But, you know, high level, that's pretty much the gist of it. That's basically all it's doing. It has a runtime component. It stores metadata. It has these things called poison red zones where, you know, whenever your program tries to access those zones, it gets flagged. And it can throw errors depending on, you know, what the situation is. It uses uses an eighth of your program's memory to store all this metadata and information. It replaces malloc, so it has its own allocator, and it wraps it with, you know, those red zones and other instrumentation things. So that's basically what this thing does. And then they talk about how to tune it up. Like you can modify the quarantine size, the depth of the stack unwinding, the size of the heap red zone. Because the problem is that if you're in like a giant program and your system has limited resources, this thing could actually end up really bogging it down. And so there are flags you can actually pass that allow you to modify that and sort of change settings. And so I'm going to show you those flags real quick and the page to get to. I'll put that in the description also, because it's not really that straightforward how you set this thing. How do you configure AddressSanitizer? You know, a lot of people don't really know. They just kind of run it vanilla. I'm trying to move this window over here. So if you go to this page here, github.com/google/sanitizer/wiki/AddressSanitizer flags, it gives you the compiler flags you need to use in order to use it. But it also tells you that you can set, there's this flag called ASan options. So you're basically just going to export ASan options, or you know, it's an environment variable, and you're just going to link a whole bunch of these guys together. So you can modify the quarantine size and megabytes, the red zone, max red zone, report globals. You could tell it to, you know, look for memory leaks or not. Allow user poisoning. So allow user poisoning is actually interesting. So the programmer could actually, or you could essentially go into the program and put in some AddressSanitizer macros and then allow user poisoning true. And then you can manually poison different areas of memory rather than having AddressSanitizer do it. See, there's just a whole bunch of options here. And in the next video, I'm actually going to show you some of these options and why you need to use them in certain circumstances. So one example is if you want to instrument a program with AddressSanitizer and then get a core dump, you have to set some of these options. Otherwise, AddressSanitizer is going to abort with exit code 1, which will not, by default, trigger a core dump on Linux systems, which is really annoying when you need to actually go and look at the state of the memory, because there's no way for you to access the memory once AddressSanitizer has aborted the program unless you do this. So I'm going to talk about that in the next video. So thanks for watching. I hope you enjoyed this. It was actually pretty fun learning about this thing, and it's a pretty cool tool. So If you enjoy this stuff and want more content, don't forget to subscribe and perhaps even hit the little notification bell. All right, thanks for watching. See you next time.